Shining light on quantized energy levels to avoid the catastrophe. Continues quantize Continues to quantize the experiment is considered a historical walkthrough, a walkthrough through the history. But in 2024, we have much better and accurate methods for timing the light beam to discover that black body is not continuous. And this was shown um, But first discoveries were found with black body emitters with Wayne's proportionality constant, which the value is shown below. And finally, to the mathematical relationship of quantized energy levels in one electron system, where it could show that the solution to the ultraviolet catastrophe was Planck's black body shown in equation 3 that includes Planck's constant based off Wayne's constant. More on quantized energy is shown here, and these are two fundamental equations. Equation 3 with the Rothenberg hydrogen isotope term, and how to calculate Rothenberg's constant with Planck's constant and the vacuum permittivity, reduced mass, the mass of an electron, and the speed of light. And here is the reduced mass of Rothenberg's constant, and with a ratio of the Rothenberg constant from hydrogen and deuterium, you can calculate the nuclear mass of deuterium. So two hypotheses were shown above in this slide. And the support for the first slide is that the effect of quantization to reduce the contribution from high frequency oscillators being significant enough to excite is not energetically available. So being that significant excitement is not energetically available. And then support for the second hypothesis is that the three peaks found for H1 and H2 will have less than a 5% percent ratio. So these two hypothesis will be discussed later in the results to see if they were upheld with experimentation or failed with experimentation. So first, the methods were shown here for the speed of light experiment by measuring the time difference between the two peaks and the distance that the light traveled, the speed of light was determined. Now the speed of light results at a variable distances, starting at below 1 meter all the way to 25 meters, the time difference between pulse peaks were shown. And as the distance from the cart, the distance that the light beam traveled increased, the difference between the peaks changed. And as the distance became greater, as the distance began to increase, the speed of light began to become closer and closer to 2.998 times 10 to the 8. So the averages were taken from all five distances, and the speed of light from that was found to be 6.5 plus or minus 4.7 10 to the 8th meters per second. This value itself was used in subsequent line spectrum analysis. Shown in the figure is the oscilloscope data at 13.11 meters total distance traveled for the light beam. Now, a different type of analysis was done to find the speed of light, and that was done by a slope analysis generated with an Excel plot. So you can see that on the y-axis we have total distance, and on the x-axis we have change of time of pulse peaks. in seconds. And it's found that uh, the speed of light was 3.10 times 8, 3 times 10 to the 8. Moving on to the black body experiment, since we were able to find the speed of light, we wanted to, well, since we were able to find the speed of light at variable distances, now we can find um, an emission spectrum over a varying amount, a varying wavelengths to see if to to see their emission spectrum and to get an idea if what we are seeing as an emission spectrum is um, a black body emitter or not. Um, so the black body emission results, uh, we have the peak intensity at 0.98, and then the peak wavelength max at 6.1286, plus or minus 77.15 nanometers. And on the right-hand side, we have figure 6 with an Excel-generated emission spectrum of, of the first light sample, which was the compact fluorescence light bulb. Uh, and the orange curve is the Planck's equation, equation 3 shown in the beginning, that was overlaid over the emission spectrum. Now, I want you to keep in mind that the compact fluorescence um, spectrum will not look the same as the other emission spectrums. And remember that for the results, for the discussion portion of the second sample was an LED light bulb. Now the peak intensity here was 9.3 plus or minus 1.7 relative. The peak wavelength max was 607.47 plus or minus 7.5 nanometers. And as you can see, the blue curve is the emission spectrum. The orange curve is the Planck blackbody intensity dependent upon the wavelength. Um, More on results, the incandescent light bulb had a peak intensity of 0.8 plus or minus 0.7, peak wavelength max at 612.8 plus or minus 70.15 nanometers. And for all the light bulbs, we calculated the Planck temperature with the orange curve. It was fitted to best cover over the blue curve itself, which was 0.47 plus or minus 0.68 times 10 to the third Kelvin. And that number is also expressed in uh, Celsius for Wanes. And now the sun on the ground taken with our photo octave table because it was a sunny day. But the peak intensity was 0.146 plus or minus 0.72. And then the peak wavelength max was 496.28 plus or minus 77.15 nanometers. And then the Planck temperature and the Wane's temperature are both shown here. But keep in mind that these are temperatures of the sun. And the temperature of the sun is about 14 billion, 14 million degrees. 14 million degrees. And here is sun data taken from outer space, given to us from the instructor from NASA. And the peak intensity was 0.25 plus or minus 0.7 relative. And then the peak wavelength intensity actually shifted to a shorter wavelength of 450.50 plus or minus 77.5 nanometers. And then the Planck temperatures and the Wayne temperatures were reported with the Wayne temperatures being higher. But keep in mind, these are not reflective of the actual temperature of the sun, which is 14 million degrees Fahrenheit. So we're moving on to the spectrum emission of the experimental methods. Now, since we completed our black body emission and we've seen that um, the compact, the CFL bulb gave us discrete peaks, we used a hydrogen deuterium lamp that will give us discrete peaks, or it'll show peaks of the H1 and the H2 to calculate to see which wavelengths they come out at. And here's the setup of the line emission experiment. And here's the line spectrum results. Please disregard the last row, but as the relative intensity increased, um, as the wavelength increased, the relative intensity increased. And please disregard the last row. And here is the results for both the first scan and the second scan. And the scan was done at a starting wavelength of 33,800 angstrom in ending wavelength of 4,900 angstroms. The first scan is orange and the second scan is blue, which will be representative throughout all the rest of the results. And as you see, I had to zoom in to the peaks to find all 14 peaks. So right off the back, the hypothesis failed because I was expecting 3 peaks, and I was not, and it failed. Now, a relationship that was shown here was that as the reduced mass increased, the wavelength decreased. So as as we know from our literature values, is that deuterium is twice the mass of hydrogen. And as you see, it there's still coupling. So there's still coupling of the peaks. And in figure 16, from left to right, both the wavelength and the peak intensities are shown and the colors are respective from the beginning full spectrum. And here are the line positions to determine the Rothenberg constants for both hydrogen and deuterium. And here is the linear fitting of the H1 Rothenberg constant, 1 divided by the wavelength dependent on the 1 divided by n squared parameters. And the R squared was reported as 0.995. And the Rothenberg constant was found by multiplying the y-intercept by 4. And the theoretical values were calculated with equations 3 and 4 from the introduction. And please take note of how the percent errors were very high, which we will discuss further in the discussions. Now, the discussion of light, the longest distance, the longer the distance, the better the speed of light agreed with theoretical values. As you can see at 24.3 meters, the percent error was 0.38. However, the percent error decreased with doing a slope analysis, getting a linear regression done with a plot that was generated in Excel to get a speed of light of 3.002 plus or minus 0.037 times 10 to the 8, which had a percent error of 0.12%. So the black body discussion, the first bulb was not a black body emitter. If you remember the compact fluorescence light bulb had had sharper peaks, and it wasn't like a smooth peak like the LED or the final light bulb that was done, or the sun for that matter. Motive to do the line spectrum experiment. Now the bulb 3 emitter had a percent error of 0.1, but the Planck fitting was done by matching Wayne's with adjusting until optimized fit. Great estimations for the bulb, but not the sun data. And the reason why they weren't good for the sun data is because the sun itself is not like a black body emitter. The sun itself creates its own energy from its core and it emits its energy out into outer space. So it's not like the typical black body emitters that we see on Earth. And bulb two is an LED, so they function on P and N junctions, taking electrons and converting it into photons across that junction. Not a black body. Now, the incandescent in the suns has best fitting for the Planck equation, which can be shown in the green boxes. Now, the discussion for line spectrum can be shown that the the Bohr energy is not reflective of the Rydberg energy. And the main reason for this is that um, the Rydberg energy has a quantum mechanical treatment of Rydberg, which can be seen in the E to in the exponential term that was used with Planck's constant, the Boseman's constant, and the speed of light. Um, and even though we were able to calculate both energies, both these models unfortunately fail to calculate the energy of multi-electrons because the models themselves are only set up for um, one electron problems. For multi-electron problems, that's left to um, Schrodinger's equations and Huckel's molecular orbital model. If you have any questions and concerns, please email me and thank you for listening. Ciao.